Hello everyone, welcome back. Today's lecture number 9, we're going to be covering SQL database scaling. Last time we kind of introduced this topic by talking about storage, and in particular relational databases. Remember, I'm using the term SQL database and relational database interchangeably because SQL is the standard query language that's used in relational databases. Last time we talked about the generic challenges of persistent storage. One of the challenges is that we have to deal with much slower performance on disks compared to operating on data that's in memory. We also have we lack language level support for accessing persistent storage, so it can be kind of complicated to access data. Databases are a way to make that access easier and to provide a lot of features that you typically would want to have for data that is stored in large data sets. So in particular, databases generally give scalability, so allow you to store lots of data more than can fit in memory. Persistence, the data hangs around after the program is done running. Indexing, the ability to quickly find particular data using either tree or hash-based data structures. And concurrency, the ability for multiple users to access the data at the same time or multiple programs to access the data. We mentioned RAID as a way to combine multiple disks to increase capacity and fault tolerance and performance. And we also showed relational databases as like the traditional kind of database. That's the standard. We're going to be talking more about relational databases today. With relational databases, you have to predefine the tables and columns that are in those tables as well as the keys. And that definition is called a schema. So it's like the structure that your data fits into. During operation, you add rows and read data, but the schema, the structure is defined ahead of time. And like I said before, indexes are used to quickly find data by having certain columns, having data structures that allow quick navigation through the data in particular columns. Okay, so to add to what I said last time, this diagram on the right-hand side shows a typical relational database setup where we have one machine that has maybe a couple of CPU sockets and some RAM, and it has a bunch of storage connected to it. There's limited I/O bandwidth between the CPU and the storage. There's also high latency when you're accessing data on storage. So you have this RAM that's on the motherboard or connected to the motherboard that is like much faster than disk, perhaps 100,000 times faster in terms of the delay before accessing, the latency. But the capacity is generally a lot smaller, maybe 100 times smaller. So when you're using a database running on a machine like this, you would want to store as much of the data you're using as possible in RAM. So by caching the data that's stored on disk, you need the data to be on disk so that it's persistent, because when you turn off the electricity to this machine, anything that's in memory will be lost, whereas disks are persistent devices that store data without electricity. But while it's operating, you want to cache as much of data as possible in memory. And so, ideally for a database to get good performance, the active data set should be smaller than the RAM size, but there also are other applications where that's not really possible, but you still might use this kind of a relational database with a single machine. For example, if you're doing like what's called an OLAP application, or data warehousing, online analytics processing, where you have a ton of data and you're doing queries that are like not to serve particular users accessing a website or something, but just to do an analysis of, let's say, a business's operations. Those things can take a long time to run, and it might go through a lot of data that's stored on disk. But the database software itself manages caching of frequently used data and important data in memory. Also, the operating system itself will automatically store the most frequently accessed file data in memory, and that happens automatically. So even when you write your own programs, like let's say you're using a simple programming language, you're using like Python or Java or whatever to write your program, and you're opening files, reading data from files. If you're doing that kind of stuff, like the first time you use the file, the access will be slow. But if you continue to read and write to that file, you'll notice that actually the performance would be improved. And like maybe the second time you run the program that accesses the file, it'll be a lot faster. The reason for that is that the operating system is automatically caching frequently used storage sectors in memory. So it actually can open the file without taking the time to access the external disk, because a copy of the file's data is actually stored in memory. Anyway, but the main topic of today is talking about how to make relational databases or SQL databases scalable. We'll find that there's a limit, but we definitely have a lot of strategies that allow us to use relational databases for some pretty large systems. Okay. In later lectures, we'll talk about NoSQL databases that are even more scalable, but actually it's rare to find applications or to be working on an application where truly you need something bigger than a relational database. So the strategies we're talking about today are quite useful in practice for the majority of applications. All right. Now, on the right-hand side of this diagram, I am showing an overview of a traditional three-tier service architecture where we have requests coming in from the client on the top. They go to a load balancer. The load balancer hands off the request to one of several clones of a stateless application. And those applications, although they themselves are stateless, connect to a shared database to store data that is kind of globally available. And that's a single database that's shared by all these stateless app instances. Okay. And that's a good design, but it creates a performance bottleneck in the database, right? Because as the system gets more load, we can add more clones of the application to run the code here, as many as we want, really, because but if we have a single database back here, that could be a bottleneck. When I say bottleneck, I mean like a factor that limits performance, because it's shared by all the requests potentially could be hitting this single shared database. Now, in this diagram, though, we see another box that doesn't have replication, and that's this load balancer up front. Now, I want you to stop and think as a review about why this load balancer would not be a bottleneck in the same way that the shared database typically would be. Okay. Well, the reasons for that are twofold. First of all, the load balancer does much less work per request than the database. So these both could be implemented on a single machine. But if all the load balancer is doing is like reading the request data off of the network and relaying it back off the network to someone else, then the only work it's doing is like copying bits in memory, and a lot of that is happening in the CPU caches. So that can happen very quickly. Whereas these databases are actually accessing data on disk. Disks are slow, or in memory, and perhaps using modifying complex data structures like trees and hash tables and whatnot to access data. So there's a lot of work going on in the database for a single request, whereas the load balancer is just handing stuff off. Another difference here is that with a load balancer, even though I showed it in this picture as a single box, this actually could be implemented by multiple machines if you're using global load balancing using DNS or IP Anycast, as we talked about before. In the load balancer lecture, you can have users that are using a single domain name, but actually through DNS would end up contacting at first a different machine, not a single shared machine that everyone is using. Okay. Now, I think that leads to another question we might ask ourselves, which is, if this shared database is a bottleneck and is being used by all the requests, why do we have it as a bottleneck? In other words, why not have many instances of the database, many clones of this database running in parallel like we have for the application server? It's a complex question, but I want you to stop and think about that for a second to see what you can come up with. As to why in this typical three-tier architecture do we typically show a single instance of a database and not scale it up horizontally by having many instances of the database? Well, mainly the reason for this is that by having many databases instead of just one, we lose the ability to coordinate through it. Right? A traditional design like this relies on a single shared database for coordination. So if a request goes into one instance of the application, for example, to create some data, like if it's a social media application and a user is creating a post, we want that post to be visible to all the users of the system. So for all the other application servers, when they're accessing data, they want to be able to see that same post. Having a single shared database is that coordination point. If all the data is there, if everyone is writing to the same database and everyone is reading from the same database, then everyone globally has the same view of the system, right? So that's a nice thing. If that wasn't the case, if we had multiple databases, then we still would have to solve the problem of coordination. There are many databases that were storing different updates of the data. Somehow they'd have to coordinate themselves. Okay, we'll talk a little bit about that today and in later lectures. But for now, this design with a single database is really helpful and clean and easy. But like I said, we'll learn some tricks in this lecture to make this more scalable by having more than one machine doing some of the work. Okay. Now, before we get to that, I want to talk about some of the other performance optimizations that are present in relational databases. So I think earlier on at the beginning of this lecture, I mentioned caching data in memory instead of going to disk every time. That's a performance optimization. Another one is in the query planner. Of course, this will be covered in a lot more depth in a full database class, which I'm not going to go into that level of detail here. But if you take as an example, the purpose of a query planner is to optimize the order of table access and the use of indices, or so that when you're executing a query, you do it in the most efficient way. Because actually, a single query could be implemented, like executed in many different ways sometimes to get the same answer, but some ways will be faster than others. As a simple example here, I'm giving a query. So I'm hoping this will make sense even if you're not like a SQL expert. But this is a system where we have two tables, the user table and a post table. So think of this as a social media application. We have users and the users have posts, and those are in different tables. What I'm trying to print out is all the posts that were made since 2010. So the post date is greater than 2010 January. And the user's birth year is less than 1920. So I want to have all the posts in the last, let's say, roughly 10 years from users who are over 100 years old today, roughly today. Okay. So to do this, I need to look at both the posts and the users. So there's some filtering happening in this where clause, both on the post table, data in the post table, and the data in the user table. Like we only want the subset of users that are quite old, and we want the subset of posts that are relatively recent. Okay, within the past 10 years, not the super old posts. So if you were implementing this query, what could you do to make this efficient? And what can you think of two different implementations, one of which would be more efficient than the other for this query? Stop and think about that. Well, what I wanted you to get to was what was the idea that you need to filter on both of these, and once you get the data from one, you check the other. But one of these will filter a lot more than the other. So, for example, in a social media application, perhaps only 0.001% of your users are more than 100 years old. So if we filter the users first to get only those very old users, that would reduce our data set immediately to a very small number. And then for those users, we can look in the post table to get all of their posts and then filter out those for just the ones in the last 10 years. That would involve very little work, especially if the index is, if both these columns that we're filtering on are indexed. The reverse approach, where we start with the posts, we first get all the posts in the past 10 years, get that set of data, and then scan through those to get the ones that are from users that are older than 100 years old. That would also work, but it's less efficient because of the statistics of the data. We know there's going to be a lot more. Probably the majority of our posts are from the last 10 years. So that's not going to really filter very much, whereas like I said, only a tiny fraction of our users are that old. Okay, so that should give you some intuition behind query planning. So your database actually would be keeping track. To do this job well, it should keep track of the statistics of the data in the different columns and make clever use of them in the query planner. Okay, that's one of the things that makes designing a database quite an interesting challenge. Okay, you have all kinds of ways to apply different tricks to speed up the system. Another thing you can do here is make use of RAM instead of disk. So you can store the most important data and indexes in RAM. We kind of mentioned that, but also the indexes. And we also, in relational databases, can do some caching. So if you have the same query being run more than once, you can cache the response and replay it if the data hasn't changed. You can kind of try to keep track of what the dependencies are for the queries, and then notice if there was a change or not to invalidate the things that you're caching, things like that. Okay, that's just a taste of relational database optimizations. Yeah, so other strategies you can use to avoid the database becoming a bottleneck, in other words, to make the database faster and to avoid the database being slow, you can reduce the number of queries that you make. So you can cache data on the front end. Wikipedia was doing that. So remember, for that Wikipedia architecture, we had these HTTP caching proxies up front that were storing the full HTML for articles that were accessed recently. By doing that, that reduces the number of requests made to the application layer, which would in turn have to ask the database to get the wiki text for the article, right? So you are actually reducing the number of database queries by having that front-end cache. Other things you can do is just apply vertical scaling. So buy a really fast machine for your database, the fastest possible. Have plenty of RAM in there for caching. If you can afford it, also get the fastest possible disks. So use solid-state drives and use them in parallel using a RAID configuration. That also would improve your performance. But just like any other vertical scaling approach, there's a limit to how far you can get with these, right? At some point, you are using the fastest possible hardware, and you need some other approach to get better performance. So the horizontal scaling approach to relational databases that we're going to be talking about for most of the lecture today is using read replicas or sharding. This is a way to parallelize the work that's happening in relational databases. Okay. So the idea of a read replica is to have like copies of the data on other machines. So instead of having just one database machine, so notice that, just as a reminder, in our architecture diagrams, we always use the cylinder icon for storage devices and especially databases. So these cylinders represent databases. And I have 3 databases. They're actually all kind of copies of the same database. We have the main database here, or the primary. And then we have 2 read replicas. Read replicas are copies of the database that can be used only for reading data, but not for writing data. So now remember, in a few slides ago, I said it was a bad idea to split up your database into multiple pieces because then you had to coordinate them. But the trick we're applying here is that we are only doing the writes in one place. Any modifications happen in exactly one place. So the coordination still is happening in one machine in some sense, like the true view of the universe is in one place. But that data is propagated to replicas after a short amount of time. There's a little bit of a delay, but basically it's consistent. So you can do reads off of any one of these 3 machines, but you have to do the writes to one place to keep it consistent. So this works because very often in many applications, a vast majority of your requests are reads rather than writes. So if you do the reads on these replica machines, you can save the capacity of the main database just for writes. Okay, so there are different kinds of queries in SQL databases, relational databases: selects, updates, and deletes. Selects are reads, updates and deletes are write operations. Okay, so any of those writing operations have to go to the main one or the primary, but the reads can happen on replicas. And these databases are configured so that the database management software is designed to allow you to specify these relationships so that the data flows downward. And actually, these arrows probably should be single directional, not bidirectional, because the data is really just flowing in one direction because the writes are happening here. And when a data is updated here in the main database, it gets pushed to the read, or perhaps the read would ask periodically, do you have any updates? Maybe that's why the arrow is bidirectional. Okay, so notice a couple things here. There's a little bit of a time lag, so it's not perfect coordination, but it's pretty good. You're never going to see inconsistent state if you're looking in one replica, but if you look at 2 different replicas, you might see that one of them has gotten an update, the other one has not. If you look at one replica, the worst thing that could happen is that you could be seeing a slightly old view of the system, but it is still a consistent view of the system that made sense, let's say, half a second ago. So but for most systems, this is okay. Like if you're talking about Wikipedia or like a social media system, like if you get a slightly old view of the system of the data, it's not a terrible thing. If you do have some data that needs to be totally up to date, 100% sure, then you could actually do the read to the main database. Like for example, if you are implementing some kind of a banking system or like, PayPal, something like that, you would want to know that your balance is really up to date. So then using this kind of read replication would probably be a bad idea. You'd have to do everything in a single database where you were sure everything was consistent. The other thing I want to point out here is that by having read replicas, you're saving the main database from doing the work of reads. Like you're pushing off the read work to these other replicas. We also are adding some work to the main database of propagating updates to the reads. And that amount of work is going to be proportional to the amount of writes. We'll see that in the next slide. So with that in mind, I want you to stop and think about what might limit the number of read replicas you can have for a relational database. Well, there are a couple of things. What limits the number? I guess the points I have here are what the downsides are of this approach. This is not an infinitely scalable approach because all the writes are going to a single database, right? So you do have to have a single machine that's capable of handling all the writes, this primary. So it's a bottleneck for writes, and it's also a single point of failure. So from a reliability perspective, this design doesn't meet every goal that we would have for the system. But more to what I was asking, what limits the number of read replicas is, I think, I have a little extra math exercise here that comes to the conclusion that the number of replicas you can have really depends on how many writes you have. Okay, because the more writes you have, the more work this main database needs to do in replicating its data to the reads. So whenever there's a write, that needs to be copied to all the read replicas. So the exercise is as follows. If we have n replicas, then every time there's a write, there's actually like n times as much work that the main database needs to do. That's basically the crux of it. So instead of just writing the data once, here the main database also needs to send n copies of that data to the replicas. So in some sense, this design with read replication creates less work for the main database to the extent that it doesn't have to handle reads, but it creates more work for the main database in the sense that every write is amplified by a factor of n. Every write takes n times as much work because of the copying that needs to be sent. So when you balance those two, you find that the optimal numbers of replicas is directly proportional to the ratio of reads to writes. So for example, if you have 10 times as many reads as writes, then you could have 10 read replicas and one one primary, and that would be balanced, right? Because for every one write, that write would actually be 10 times as much work because it needs to send 10 copies to the replicas. And so the main database in that case would be doing 10 work units. The replicas would also be doing 10 work units because, like I said there were 10 times as many reads as there are writes. Okay, so that would be a balanced system. So that'd be a system where both the primary database and the read replicas were at full capacity. They would reach full capacity when the ratio of reads to writes is the same as the ratios of read replicas, the number of read replicas in the system. Okay. So with that in mind, do you have any ideas for making this more scalable? Remember, I said that the problem here basically is that we're limited in the number of writes that the main database can handle because every write is amplified n times by the number of read replicas. How can we reduce the amount of work that the main database has to do for writes so we can scale this up to a bigger system? Well, what you might come up with is a way to have their primary database not send n copies, but a smaller number of copies. In the best case, it could send just one copy. In this case, I'm showing a two-level hierarchical replication system where the primary database is sending 3 copies of its writes to these middle replicas, and then those middle replicas are sending 3 copies to the read replicas. So we have 9 read replicas, but the primary is only doing 3 times as much work for every write as it would have to do if there was no replication. Okay. So in some sense, this is a more scalable design. We get more read and write scalability. We can have more replicas without reaching the limit in this primary database of the number of writes it can handle. And you could also imagine an even some sense better design would be to have your primary database connected to just a single replica, and that single replica would be in this position of fanning out to other replicas, and you could kind of and then the amount of extra work the main database would be doing would be only 1 time, so it would be doing just double the work instead of, like in this case, 4 times the work for every write. But to understand this, I want you to stop and think about where the read requests would go with this kind of a database replication scheme. If your application needs to read data, who should it send those reads to? Well, it should go to the bottom level of this scheme, right? There are 9 of them. So there are 9 read replicas that have a full copy of the data, and they can handle any read request. Because whenever data is updated, it's propagated downward until it reaches these leaves in the hierarchy. Why not read from these middle replicas? What do you think? I mean, technically you could do it, but the problem with that is that these middle replicas are not going to have as much extra capacity as the leaf replicas, because these middle replicas are doing the extra work of propagating every write to children. So if you do that, you'll start to slow down the ability of. That's not the most scalable approach. That's similar to reading from the primary, right? Because these middle replicas are handling are duplicating all the writes as well as whereas these leaf replicas are only handling every write once. These middle replicas are handling every write 4 times, so they have less spare capacity. Okay, where do the write requests go in this system? Which of these can handle a write request? I mean, technically you could send it anywhere, but it would be a mistake. You have to send it to just this one primary machine. Only by sending to the primary machine will the modification you're making, that edit, will get sent to every single other replica in the system. We want everything to be consistent. Remember that. We want all the machines to have a full copy of the data in order to allow us to do the reads from any one of these read replicas in the bottom level. Now, finally, can we add more replication levels to the system? So here, this has 3 levels. Can we add more levels to get more scalability, to handle more reads, let's say? Would that allow us to achieve an arbitrary number of read replicas by adding more levels? Well, yes, you could do that. I guess I should also ask what's the downside of that, but I've answered it here. You can reach an infinite amount of read scalability, but every time you add another level, there's more delay between the writes and the reads. Okay, so there's a trade-off there between the read scaling level and the delay between writes and those being visible at all the replicas, right? Because you have to propagate more hops from the primary to the replicas. Okay. All right, so what I'm describing here and in the previous slide to a lesser extent is a kind of horizontal scaling for database reads. We have many different replicas we can choose from to make a read request from. Now, the writes were not really scaled. I guess there's a little bit of benefit here because in a traditional design with a single database, that one database machine would be handling the reads as well as the writes. So there would be, whereas in this design, the machine is dedicated to just doing writes. So there is some like extra capacity there for writes, but it's limited still to just the capacity of a single machine. So we wouldn't really call that horizontal scaling for writes, but we do have horizontal scaling for reads. Okay. Now, once we design that though, how do we really use it in practice? I want to show a little bit more detail. So in this diagram, I'm simplifying the primary. I'm showing just a single level where you have a primary database and a single child layer of read replicas. That's okay. This also could be multiple level. It doesn't really matter, but I'm just showing a single level. Okay, so we have 9 read replicas, 1 primary. To make use of this kind of a system, we have to send a request to do 2 different kinds of places, depending on whether the reads or writes. So the writes, if our application is here in blue, all the writes that it makes are going to this primary database. So these are the SQL inserts, updates, and deletes. All the reads have to go to a read replica. Now, we have many to choose from, so we stick a load balancer in front of these read replicas, right? This could be a NAT type load balancer, similar to what you might use for a web server, something that just operates at like the network level. So that on a per packet basis, I think what's called a layer 4 load balancer. It could also be a software library. Okay, so this choice of where to send your data and your choice of replicas could be done in software. So I'm going to show you a little library that I wrote for one of the websites that I develop here. So this is Java code. The class is called Tomcat DB cluster, and this is just a helper class to allow the rest of the code to access the database through a kind of software-based load balancer. And this class has internally a list of read replicas, which are these Tomcat database objects. And it has it's using a round robin scheduler, so it has an integer for the last one that it chose. And basically, so there's some setup stuff. It's not super important, but the main thing I want to show you here down in this last function is that when you ask this object for a connection, if you're asking for a read-only connection, then it just does some math to cycle through that list of replicas, right? So it just increments the last choice by 1, and does that modulo the number of replicas here. Okay. Whereas if you ask for a this is for getting read-only connections. The superclass of this Tomcat database has a method for getting the writable connection, so it's not shown in this object. Although I guess I could probably show it in this other file. This is the one that doesn't have the read replicas. In this case, you would there's a function called get connection that just gets the single database. Okay, but that's not super important. That's just an example of a software library that does a kind of round robin choice that cycles through the different available read replicas when it's getting a read-only connection. Okay. Now, given this design, do you see any shortcomings in this kind of a replication strategy for a relational database? In other words, where might you need something more than this? Or what kind of a system might this not be enough to solve your scaling problems or your system design problems? Okay, stop and think about that. So there are 2 big things, which I hope you came up with at least one of them. So first of all, notice that the writes are not scalable. The writes are all still going to a single machine. And so once that machine reaches its capacity and we vertically scale it as much as we can, our system can't grow anymore. The capacity is also not scalable. This is a little bit more subtle because the full data set is replicated in all of these nodes. So once you reach the storage capacity of a single machine, then your data set can't grow any more than that. Okay, because we're not splitting up the data. We're storing full copies of the data in all the nodes. We'll see in NoSQL databases we take a different approach, and also in the second half of this lecture with sharding we take a different approach. Also, this primary database, in addition to being a scaling bottleneck, is a single point of failure, which could make the system less reliable. So to address that single point of failure, I mean, you actually can come up with a pretty simple solution. I mean, it's not simple to implement, but a standard solution, let's say, is to have a standby primary that's ready to take over if the primary fails, if the main primary fails. So in this case, You have the application connected again to the primary and to the read replicas. There also is this standby primary, which is getting replications, which is staying in sync with the primary. If the primary ever goes down, the application will switch over to using the standby instead. And this could be connected to its own read replicas or the same ones. It doesn't really matter. Both are possible. Okay. All right. So finally, I mean, thinking about this, we just showed an example where we had a standby primary. Why not have more than one primaries to begin with at all times and scale the writes by sending them to the two different machines? So send half the writes to one machine primary and half the writes to the other primary. Why not do that? This is a review question. We kind of talked about this a few times already. The data would be inconsistent if this happened. So if we're writing in one place, some of the writes in one place, some of them in the other place, there'd be no one place that had like a complete consistent view of the data. Also, this doesn't necessarily solve the problem if we're still replicating to each other, right? Any one machine would still be handling all the writes, although indirectly. So when I do a write to this number 1 machine, it has to propagate that to the number 2 machine. So there's still twice as much those writes, although it's getting half as many writes, every write is involving twice as much work, if that makes sense. Okay, so there's still a performance bottleneck in the exact same way if we are sharing the data on the 2 machines. All right. So the second half topic for this lecture is about scaling writes and storage capacity. So we're going to try to solve the bigger problem of scaling this kind of database to big systems. And this is, in fact, what Facebook does to use a relational database to store data for their social network. Okay, they don't have a single primary database to handle all the writes. They don't have all the data in any one machine. Instead, they implement a horizontal scaling scheme like what we're going to talk about now. How would you do it? So how would you implement horizontal scaling for writes? Do you have any ideas, things we can do to handle the writes, scalably with this kind of a system, and also to have more capacity than is available in a single machine? The two actually go together. The solutions go together. Well, if you did the reading or you already are familiar with this topic, you might have an answer. But basically, it comes down to some kind of partitioning of the data. Okay. So I'm going to talk about 2 different ways of partitioning data. One is functional partitioning, and the other is called data partitioning, although they both are partitioning data, but in different ways. With functional partitioning, we split up our database into like sub-databases that have different functions. So we've stored different types or categories of data in different databases. Like you might have 3 different databases in your system, one for the accounts data, one for the orders data, one for the customers data. So 3 different databases. So the writes for accounts would go in one place, the writes for the orders would go in a different place, and so on. So, and there's no special software needed. You just set up more than one database, right? That splits the load, right? That works, but the downside of this is that you no longer can build queries. You now have 3 separate databases, which is okay, but if you're doing queries that want to like join data from multiple from tables in multiple databases, you actually lose the ability to do that, and that gets to be a pain unless you write custom code you write it in your own code rather than having it happen automatically in SQL code. Also, there's only a few of these functional partitions that are possible. So generally, this is limited in the greatest extent to the number of tables that you have. If you have 10 tables, there's no way to in your whole system. There's no way to functionally partition into more than 10 different databases. So it's not a highly scalable approach, but this can help, in going from, let's say, 1 to 5, 5 times as much load. The second approach is more general and more scalable, which is called data partitioning. So the first approach, functional partitioning, is splitting the data by tables. So some tables are in one database and other tables are in a different database. The second approach is dividing the data by rows. So we still have the same tables in all the partitions, but a subset of rows goes in each of the partitions. Okay. We call those partitions shards. So another term for data partitioning in relational databases is called sharding. And again, this is what Facebook does to parallelize their big data set. So an example of this might be that if we're talking about Facebook, users are in different geographic regions. So perhaps we use the geography as a sharding key, which is like the data item that determines how you're assigned to a shard, which is to say a partition. So like all the Illinois data for the social network might be in one database. All the Wisconsin data is in another database. All the New York data is another database. This is also commonly done for like cloud-based SaaS applications that are where you have like different customers have their own data sets that are running in your systems, like Northwestern's Canvas system might be in one shard, a different university would be in another shard, and so on, right? So you have different machines handling the data. But each one of these is kind of its own complete system in that it has all the different kinds of data are stored in each of the shards. Okay. So sharding is usually not supported natively. So this is kind of like a hack to scale up a relational database. And generally at the application level, you'd have a library that decided how to translate from how to split your request into multiple requests that went to different shards to get your data. So an example of this I'm showing here, I'm using the names of the teaching staff from a previous version of this class. And this is the social media examples. We have users and we have their posts. So notice I have the same tables in the two shards. So the two shards are two different machines, remember. But I have different rows. I've split up the rows between the different shards. So all of like my data is in shard 0, but Clarissa's data is all in shard 1. So I have a shard key I'm using in this case is the shard ID. I mean the user ID rather. And the rule I'm using basically is that I take the user ID mod 2 to determine what shard to put it in. So you notice we have user 0, 2, 4, and user 1, 3. All the odd number users are in shard 0. Even numbered users are in shard 1. Right. So in this kind of scheme, how would you implement a query for all the posts by Steve? So this is the syntax, the SQL query for it. How would you implement that? You have two shards to choose from to access, yet you're trying to implement this query. How would you do that? Well, you'd first perhaps take the user ID and apply the sharding rule to figure out what shard you need to look at, and then you just run the query in that shard. So if you figure out that all the data is in shard 0, you can run this query verbatim in this shard. If you made a mistake and ran it in this shard, that would be wrong. You would not get the results because you didn't understand the shard rule. You made that mistake. Okay, so another example, this is more complex now. If we're taking the social media example, we don't just have users and posts, but we have like friendship relationships between users. So for every user, we have multiple rows that list out all the friends of that user. So Steve's friends are person 1, 2, 3, and 4. Those are all friends of person 0. Okay, and so these are like the edges in the social network, and these users are like the nodes in that network. So that the user table and the friend table together form a graph, which is a social network. And again, I have multiple shards for the data, and I'm splitting up the users. I'm sharding data by the user ID. And notice that all these tables have a column called user that I can use to determine which of the shards the row goes in, right? So like these tables are only showing the data for the even numbered users. And if you looked at the other shard, you would see the odd numbered users. So if I have a more complex query now, so in this case, I want to query for the latest 10 posts from Steve's friends. Now, if you think about that, that's a very natural query to do in a social media application, right? When I visit when I open the application, I want to see posts from my friends, right? Recent posts from my friends. So behind the scenes, a query like this would be executed. And this is how you would write it if it was a simple relational database without any sharding. But now that there's sharding, we have to be careful about this because the data is split. How would you implement this given that we have shards? Well, unlike the previous example, we can't just do the simple thing of like figuring out what shard we need to operate on and then send the query to that shard, because this query involves data from all the shards. Because I'm friends with some people who have odd numbered user IDs, right? Like the social network itself is kind of a random graph that's not going to, you can't create any shard rule that would divide the data so cleanly that only the only data I ever need is all going to be together in one shard. Okay, so I need to run a query like this on all the shards, and then collect the data together. Except I can't run exactly this because I can't do a join to the user table using finding a row called Steve, because this Steve row is only going to be in one place, only in one shard. So I need to run like a part of this query in one of the shards to get back that the user ID I'm looking for is 0, and then build another query that's similar to this, but it has user ID like post dot friend dot user is equal to 0 literally in the filter, and run that on all the shards and come back and merge it. So it's like a lot more complicated. Okay, so that was a quick view of sharding. So it's a useful technique. The pros are, because we're storing every row only once, we get a lot more scalability. We get more capacity, right? When we have like 10 nodes now, if we're sharding now instead of just doing read replicas, every one of those 10 only has to store 1/10 of the total data. So the capacity of the whole system grows as we add more nodes, right? The capacity scales. The data is consistent, because we're still only storing the rows in one place, so we don't have to worry about things being inconsistent. If we're careful about choosing the sharding key, the data will be balanced. So, like if, for example, doing the even and odd user IDs is a way to make it very balanced. And then we can choose, if we have an application that fits it well, we might be able to do a lot of our queries using just one or a few shards. Like, for example, if we're running a like Piazza or CampusWire, one of those classroom question answer systems for different universities, if we divide the data according to universities, then any one user accessing the system is only going to be care about the data for their university, because they're only accessing their classes. So sharding that system is very easy. There are very few cases when I visit that website from Northwestern University, yet I need to access data that's at some other university, like Duke or whatever, right? So sharding can work really well if your data like naturally is siloed, like separate. Social network is not an example of that. So even though, like I said, Facebook is using this approach, they have to be very clever about how they deploy it to make that work. The downsides are that you can't just use plain SQL to access your data. You need some kind of like libraries to split up queries and join them back together cleverly. You have to manually adapt your queries to match the sharding. You have to be careful about choosing your sharding key so that you don't have an imbalance of data or an imbalance of traffic. And most importantly, this last one, there are going to be some queries that have to access every shard in a system, and when that happens, you've lost now your ability to scale for the traffic, right? Once you involve all the machines in your requests, you're kind of in trouble. And this slide summarizes that. And this is like the end of this lecture, basically. So sharding can work well or it can work badly. It all depends on how many nodes are involved in your requests. So if we assume that there are n nodes, there are r requests per second. That's our rate of making requests. And every node has the capacity to handle at most c requests per second. Okay, those are our three numbers. And we have different assumptions. If every, that's what these last three bullet points are. If every request is sent to one node, that's the best case, because there's the least amount of work that's required, right? We just kind of have like a load balancer sending the request to one node. That load balancer might need to be aware of the sharding rule to decide who to send it to. So that the total request rate in that case is n times c. So the number of nodes times the capacity per node. So as we increase the number of nodes, n, our rate of handling requests goes up. That's a scalable system. If every request is sent to a constant k number of nodes, it's similar but a little different. So the number of requests we can handle in total is not n times c, but n times c divided by k, because every request involves is replicated k times on k different nodes. But in the big O notation, n times c over k is still big O of nc. if k is just a constant. Like k might be 3 nodes. If you have to involve exactly 3 nodes in every request, that's unfortunate compared to just involving 1, but it's still scalable. It just means you need 3 times as many nodes. But if you keep adding 3 nodes, every time you add 3 nodes, you're adding a factor of c to the amount of requests that can be handled. So that's still scalable. Okay, involving 1 node is scalable in every request. Involving a constant k number of nodes in every request is also scalable. What's not scalable is this final case where we send the request to every single node. If our request has to involve every node in our system, then adding more nodes doesn't help, because by definition, you're just adding, every time you add another node, you're also adding more work that needs to be done in total for every request, although you're also in total doing more work in some sense. Right, so the rate of requests is just going to be equal to the capacity of a single machine, because every machine needs to be handled by every request needs to go through every machine. That doesn't, as you increase n, this value c doesn't go up. Cool. So which of these situations we are in for a sharded relational database depends on our sharding rule and our dataset structure. So if the first examples I gave where we're only looking for the data of a particular user and all that data was in one shard, that was the first case, very scalable. The second case, where we had a social network, we wanted to get all the posts for my friends. If my friends are distributed across all the other nodes in the system, all the other shards in the system, then that would involve all the nodes, and that's not scalable. Now, in reality, maybe you can be clever about the sharding so that typically the data that I need is in a small number of shards, and that's what you want to do with you want to be clever about your data partitioning so you achieve something that's more scalable as opposed to not scalable. It's not always possible, though. Okay. So to summarize this lecture, we introduced read replicas for relational databases. That allows us to horizontally scale the system to allow for more reading. Writes are still done in one place in the primary node. They're propagated to replicas. The data in the replicas might lag behind the primary, but it's self-consistent. And this idea works well because very often writes are less common than reads. So you really are focusing on handling a lot of reads. We did have some approaches to handle lots of writes in a scalable way, which is to partition the data either functionally, or which is putting different tables on different databases, different machines, or through data partitioning or sharding, where you put different rows in different machines. Sharding works well for queries that if we can shard in a way such that the queries are handled by a single machine, a single shard. If not, then we involve a lot of machines and we don't get the scaling benefits. Okay, so next time we're going to be talking about NoSQL databases, which are ways to get even more horizontal scaling. The downside is that we'll lose some of the analytics capabilities and the rich syntax of SQL in the process, but a lot more on that later. So see you later.